let's proceed. I would like also to, for today, I would like to have time to say two more things. First of all, we will often need Sartre's theorem. I recall what it is. That assume that you have not a function but an arbitrary smooth map from a manifold of any dimension to a manifold of any other dimension, and then a critical point for a function. A critical point is a point where the differential is zero. For a general map, a proper definition is that critical point is a point x such that df of x is not df at point x is not surjective. So rank of the differential is smaller than n. It is important that smaller than n, not than m. So, for instance, if you have a map from a circle to R3, just a knot, yes, then all points are critical, just by definition, since we cannot have a surjective. So if m is less than n, then all points are definitely critical. And this is a critical point, and there is the following very nice notion of a critical value. Critical value is just f of x, where x is critical. So critical points, f is critical point. Critical points live here in M, critical values live in M. And Sartre's theorem says that for any smooth f, not for generic, not for just for any smooth f, the Lebesgue measure of the set of critical values is zero. So the Lebesgue measure, it is in n. Well, so the Lebesgue measure of this set of critical values. What does it mean? Actually, to understand this theorem, you don't need anything about the Lebesgue measure. It just means that you can cover this subset is rather small. You can cover it, but union of countably many balls with arbitrarily small total volume. For any epsilon, you can find countably many balls in n. For any epsilon, of course, for any measure, for any metric of n, you can find countably many balls of arbitrarily small volume, such that they cover all these bad points. Actually, this theorem is usually used to prove that there is to get at least one non-critical value. The most important part is that non-critical values always exist. But actually, it is true that just there are very few critical values. Okay, let us prove it. It has really a nice and short proof, and then apply it to worse functions. The proof I want to, there are many different proofs. This proof is a version of Kontragin's proof simplified by Miller in one of his papers. The only thing which I need to know about the back measure here is the following Fubini theorem. Assume that you have got a subset in RQ, and this RQ I would like to consider it as R1 cross RQ minus 1. So this RQ consists of these linear subsets RQ minus 1. And assume that the intersection of my set X with any S n minus 1 dimensional measure 0. Then Fubini's theorem says that n dimensional measure of X is also 0. This is the only result from measure theorem which I need. It is not so hard. And maybe not to spend a lot of time, I will be rather quick in this proof, and you may fill in details if you like. The idea is as follows. Let us consider the set of all critical points of F. Let us denote it by C. Well, first of all, of course, these properties of finitely back measure behave very nicely with respect to countable unions. So, of course, we can easily restrict to an arbitrary coordinate chart here and to an arbitrary coordinate chart here. So actually, the theorem will follow if we prove it for a function. This is a local theorem. We can prove it for a function on an open set in Rn to just Rn. Here we do not need to consider any global situation. The idea is the following, that let us consider the set of all critical points. This is the set of all critical points where the differential is not surjective. And let us consider the following subsets here. Look, critical point is a point where the differential is not surjective. The C1 is the set of all points where the first differential is 0. Not a full run, but here it's just 0. Well, C2, what does it mean that that the differential is 0? This means that all partial derivatives are 0. Here we assume that all partial, so in CP we assume that all derivatives, partial derivatives, up to order P are 0 at this point. So we have such filtration. And the proof is in 3 steps. First of all, step 1, let us, we would like to prove that the measure of f of c is 0. Well, let us first prove that the measure of c minus c1 that this set has 0 measure. This would be first step. Step B will be that for each k, such a difference has 0 measure. And step C will be that, okay, we could consider the intersection of all of them, but actually it is enough to say that f of ck has zero measure for sufficiently large. So these are 3 steps, and let us perform all of them. Yes, in all steps, of course, I will use induction by m and n. So I assume that for smaller, it is enough to say that for smaller n, the theorem is proved. Base is trivial. So, assume that we are in C without C1. This means that our differential is not surjective, but there is at least one non-trivial derivative. Without loss of generality, we can assume that the derivative by x1 is not zero. Then let us make a coordinate change. I can take by implicit function theorem, I can locally take this for the first coordinate. Well, so in other ways, I can consider such local diffeomorphism. Well, here we have our map F, and here map F becomes just the first coordinate. I'm sorry. I too hurry. Of course, one of partial derivative is f is not a function. F is a map. So one of derivative is non-zero. This means that one entry of the matrix of derivative is non-zero, and let it be f1 for x1. So that here is f1, and here what I mean that this is some map, but its first coordinate it is just it goes to y1 something. Critical points here and critical points here are the same. This is just change of coordinates. So critical values of f and g are locally the same if I want critical values in the neighborhood of this x. Well, then they are the same. But what can we say about the differential of this g? The differential of this g is the following form. Here we just have first coordinate, and here we have the differential of this g on every level. Yes. So a point is something here is critical value when it is critical value for the restriction on a level of the first coordinate. And by the inertial hypothesis, every such restriction has measure 0, and so by Fubini's theorem, we have measure 0 in total. This is locally, but if we have measure 0 in the neighborhood of any x, then we have totally measure 0. So this is step A. If we would like to have step B, then we need to assume that, so we are interested in ck without ck plus 1. What if we have a point here, what does it mean? That all the partial derivatives of up to order k are 0, but at least one partial derivative of order k plus 1 is not 0. Let it be, so we have one of these one of this is non-zero. Again, without loss of generality, we may assume that this is 1 and that this is 1. Then let us consider the following function. Take the same derivative without this dx1. Then this guy has non-zero derivative along x1, and so by implicit function theorem we can take this one for a local coordinate instead of x1. So we have to take local coordinates. Again, we can pass from the initial local coordinates by some differential h to this w, x2, xn. What can we say in this situation? How this set ck without ck plus 1 looks here. So we are interested in those points where we are interested not in critical values, we are interested only with we are interested with points in f of ck here. What does it mean that we are in ck? That all derivatives up to the order k is 0 at this point. But look, in particular, this means that this is also a derivative of order k, yes? So it must be also 0. So in particular, all our f of ck is completely, again, it is a local statement, that it is locally contained, let it be g, in g of 0 times any coordinates here. If the first is non-zero, then we definitely have a non-zero. At least this function is non-zero. But look, here we need to have all other coordinates also 0. All other derivatives are also 0. So these derivatives are also, all derivatives with respect to these coordinates. Let us fix this coordinate. And all derivatives with respect to that coordinates are also 0. So we at least have critical values, the corresponding map. I don't want to explain it further. This is a good exercise to check that. Well, we again are in the situation of this theorem, Sartre's theorem for smaller n. So we again have measure 0. Well, and third step is purely analytic. Almost no geometry. That it is true for sufficiently large k. Why? Well, let us consider what does it mean sufficiently large? Sufficiently large means that that it is k is greater than m over n minus 1. Let's assume that this is true. Then, well, again we can consider the situation locally, so we can assume that the image is inside some compact cube. So we can consider some compact cube in the image. Well, and also what we have in a compact cube. assume that you have here, first assume that you have one estimate. Assume that you here have a small ball, not here, ball is here. A small ball, or compact ball, which is contained in this U. Then I can write down Taylor's expansion for F. It is very easy to write down Taylor's expansion since all our derivatives up to k are 0. So I just like to say that if I write x is centered here and I would like to write f of x plus h, then it is just f of x. And now I have some remainder. What I can say about remainder? It can be estimated by this is remainder. This remainder is estimated by some constant by h to the power k plus 1. That's all what I need from Taylor's expansion. And this constant, again, by taking, if this ball is compactly contained, then this constant is the same on the whole. Actually, I may assume that this is some absolute constant. The matter is that my set is exhausted by subsets with various constants, and if the measure of each of them is 0, then the measure of the union is also 0. So I may consider that this constant is 1 million, some absolute constant. That's all what I need, but now an easy argument is as follows. Let us study, let us take here some cube, and I would like to study the measure of the intersection with this cube, or f of ck. If it is 0 for any cube, then it is 0 total. So let us consider this cube. But now I would like to decompose this cube into small cubes. Just decompose it into cubes of size delta, linear size. How many cubes are here? It is constant times delta to the power minus n. Well, all constants are different and are absolute constants. I do not want to think about them. There are as many cubes. This is number of small cubes. How many of these cubes intersect with our set f of ck? It may happen that all of them intersect, but let us consider one of them which intersects. So in this this is that small cube. Here I have a point which belongs to f of ck, and this small cube, let it be sigma. I would like to consider an estimate for the measure of the intersection of this set of f of ck with cube sigma. What can we say? We can say that, look, when we are inside this set, then I would like to consider point x plus h here. X is this point, and h can be written as, it is again some constant times delta. This is very easy constant, this is just square root of n. But it is some constant. Well, so let us look here. If Sorry, I do some strange thing. Sorry. X is not here, but X is here.
Yeah.
Oh. One moment. It was too optimistic. Ой. Sorry. I'm very sorry. In my preparation, n was the dimension of this, and so I everywhere dismissed, missed, в общем, перепутал лево и право, извините. Sorry. We here in U, we consider some cube. Cube is on the left. I would like to prove that the image of this cube, I have here some small, large cube I. I would like to prove that the measure of the image CK, of the intersection of this I. Here in I have some bad points which are in CK. I would like to prove that the measure of these points here is 0. If I prove this for any cube, then it's okay. I'm done. But cube is on the left. Cube is m dimensional. So when I decompose it into small cubes, there are as many of them. It's delta minus m. Well, not m. Now I consider this small cube. This small cube is here in U on the left. So if I take a point here, x, and I take another point, I take a point which belongs to CK, not to f of CK, but to CK. And I consider another point which also belongs to this CK. Well, then what can I say? Of course, I can say that I have this estimate. This constant is just square root of m. This estimate which was written here, that f of x plus h minus f of x is less or equal to some constant times h to the power k plus 1. This is true. That's okay. So I would like to apply this. Applying this, I say that, look, f in this equation, f of x plus h minus f of x can be bounded by some constant times delta to the power k plus 1. Okay, but now I say, okay, but all these x plus h so are contained in a ball with centered at f of x with this radius. So the measure of all such f of x plus h, the measure of such f of x plus h is bounded by some constant. This constant is raised to a power, something else is multiplied by them, but it is constant times, it is n-dimensional ball, it is on the right. So we have delta to the power n k plus 1, like that. Well, that's good. Look, but this is for any of these small.
Sorry,
Yeah.
should this n be n instead? Delta to the power of n times k?
No, no. Look, I measure
Yeah, that's
the ball here.
yeah. That's
This
the
ball
measure-
is on the right. This ball is in Rn.
Yes. Yes. Okay, so its measure is constant times
Delta
delta.
to the power n. But
Ah,
times radius to the power
okay.
n, but radius is like that.
Yeah. Okay.
So this is exactly as here. But now what I can say, but how many of these, this is for one single cube. I measure only those f of x plus h, which such that x plus h is inside this cube. And its measure is like that.
Yeah.
But what is for the total measure? I must multiply by the number of cubes. So total measure, total measure, I mean this one. Measure of f of ck intersected with this large cube. It can be bounded by some constant, this constant and this constant, together give a constant. And here I have delta to the power n k plus 1 minus n. And now if k is large enough, I need this. If k is large enough means exactly that I would like to be less than m over. Sorry. Well, I want k to be large enough to have that this is negative. Oh, positive. And of course I can take k large enough to yeah, so k is greater than m over n, or something like that. If it is true, then this tends to 0 if delta approaches 0. But delta we can choose it whenever we want. So this is some absolute constant, and so we get it. Actually, this has 0 measure under this, and this finishes, this is the proof. Well, so this is about Sartre's theorem, and this finishes its proof. And how Sartre's theorem is applied? The matter that until now we do not know how to construct a Morse function on a given manifold. So a good question is whether Morse functions exist. What is an easy source of Morse functions? An easy source of Morse functions is as follows. Let us, first of all, I hope that you know, if not, then it's an easy exercise. that if you have a, say, compact without boundary manifold, then it can be embedded in some large Euclidean space. There are also some restrictions. It can be embedded to n dimensional vector space, but it doesn't matter for me. For me, it is only important that M can be embedded in some R and capital with a rather large n. And then, what is a natural source of functions on M? Suppose that let us identify M. So we can consider we can consider arbitrary linear maps to R, just linear functions. And we can consider the compositions as functions of phi. So, what is a linear function? A linear function is an element in home from R n to R, well, which is of course isomorphic to Rn, the dual space. The claim is that for all L except for a measure 0 subset, the resultant function is Morse. So almost always this is a Morse function. So proposition is that for all A of some measure 0 subset of Rn, the function A composition with phi is Morse. How to prove this? The matter is that let us consider let us consider just the direct product of M with the set of all such A's. So here lives a point in M, and here lives a linear function. And of course, this construction yields sorry. No. Что? Well, спасибо. I need to leave. Василий will proceed with it. Спасибо. Я тороплюсь уже. свидания.
До свидания.
So yeah, let us prove actually a little bit more general statement that let me rephrase it. So yeah, it will be position. Right. Yeah, it states that if so let f we didn't have it is some function, okay, from m to r. Well, just smooth. And then we state that for almost all linear functions a, the sum, we can sum f plus a and consider it as a map from m to r. Okay. That will be worse. Okay. So it's just this proposition is the game is when f is 0. This proposition f can be 0, and we will prove this a little bit more general statement. So yeah, now we consider m times. So we need some diagram. We consider m times these whole spaces. So it's space of our linear functions. And here we have let it will be w, which will be pairs xa such that differential of so f plus a and the point x is 0. So we want to control critical points. So this manifold is just about critical points. So what we want, we have a projection to M. And a state that this projection is just isomorphic. Yeah, because what is inverse map, we take X to a pair of X, and this linear map will be just minus differential of Fx. Yeah. So this space is just isomorphic to our manifold M. Its points is it point and linear map, which is just differential at this point. Сейчас, стоп. Сейчас, секунду, что-то какая-то логика.
Будет каких-то точек, он точно сделает.
What's the problem?
Some differential. The differential. Can you see? Oh, it's okay.
Точек минимум.
Oh, it's okay. Maybe it's okay. Maybe it's okay. Maybe it's okay. Yeah. We don't require that our linear function is not 0. Yeah. We don't require this. So it can be 0. Okay, and then we have another projection. So literally to this space. So yes, this projection will be pi, and so it just to avoid xn, we do a. And let us consider this map. So yeah, what is differential of pi? So I want to say that it is just exactly the Gaussian of our map. Yeah. So, yeah. And so then you just apply like me start 1 to pi. Yes.
Excuse me, вот, когда мы смотрим на проекцию P и в обратную сторону, у нас же минус df от x это линейная функция на касательном пространстве k, а не в R точно.
Yeah, so it's very important that M is embedded in Rm. So your differential, you can consider it as just, it's, yeah, and since it's embedded in Rm, you can identify your tangent space to some subset from Rm, and so it gives you some linear function. So it's very important that M in Rm here.
Ну, то есть у нас линейная функция на Rn маленьком, которая касательно пространства? Или на всем Rn?
Сейчас. Сейчас, эта линейная функция должна быть просто чем?
You have a natural embedding from tangent space of m to the power of big N. So df at every point is naturally identified with big N dimensional vector. So what's the problem?
Yeah, I want to say that df gives a function of tangent space.
Yeah, but the tangent space itself is embedded in
Yeah, and then you should somehow. Ну, потом мы должны продолжить это все. Да, видимо, используем путем еще правильно. Правильно?
Просто, казалось бы, тогда не единственное предложение.
Правильно, вот. Потому что я рассказываю. Вот, извините, sorry, yeah. In this book it's written, In this book it's written that M in Rm, so yeah. So let me finish, yeah, sorry. It's all true if M is open. If M is open, then tangent space to M has full dimension, and then it's differential, so it's a function on tangent space. So and since if it's open, then it's of full dimension, so the tangent space is of full dimension, and then differential gives you linear function. Yeah, but here you can just take. So we should here take not M, but let's say M tilde, where M tilde, where M tilde is just regular neighborhood. So it's регулярная окрестность of M. Yeah. and then this differential is correct linear function. So yeah, why it's true? So you have such diagram, and this map, it just you take point x and matters to its minus differential. And differential of this map is just Gaussian, and its critical points. If your target is critical point, then x is not Morse. It's a degenerate point, but by some lemma, you know that the set of degenerate point has measure 0, so you take some complement to degenerate point, and then this f plus L, so it will be just, so this f plus L will be Morse. Yeah. Okay? Yeah, it's like this. Сейчас давайте, да, есть какие-то вопросы? Извините, я чуть не показал, что он был проще. Понятно?
А почему Гиссиан это, почему дифференциал это Гиссиан?
Ну, у нас прямо это выражение, so our map is x to differential, and we take differential of differential. The differential of differential, it's exactly this.
Потому что Гиссиан определен только в точках, которые критические.
Почему?
Да.
Сейчас.
Ну и если бескоординатно, то как квадратичная форма. А здесь он как...
Ну, в смысле, от замены координат зависит.
But we all are n. We are in Rn, so I think that we have some canonical coordinates since we're going here. So I think this all correct.
Ну, то, что в этих координатах сделано.
Да.
А мы функцию f тоже продлеваем на вот эту трубчатую окрестность.
Да. Но это всегда нужно сделать. Всегда нужно сделать. Окей. Okay. Yeah, and now we want to explicitly write some Morse functions. So our next point will be Morse functions. What projective spaces? Spaces. Members made. So let us begin with projective spaces. So it's RPN and CDN. And yeah, so maybe let us try to use this proposition. So first of all, first question is how to embed RPN and CPN in some RPN.
We can, the idea that we need to invent some partition of unity explicitly.
No. In coordinate, yeah. I wanted to, there is a very nice formula. In
Of course,
coordinate.
we have an explicit formula for partition.
So we want from RPN to some Rn big, yeah? So we take here a point, let us say x0, xn. And where it goes.
No, we will have fractions in each coordinate of the form, no, sum, no, square, sum, and, ну, короче, в знаменателе будет сумма квадратов в
Okay.
каждой координате.
Okay.
Вот.
Okay. We should normalize it by AI. Yeah. Okay.
И дальше мы, ну, в общем,
Квадратичные полиномы.
Все квадратичные.
можно, мы берем для каждого и икситы, и вот каждую точку отправляем в иксы умножить на вот эту точку исходную.
Сейчас мне вот идея больше нравится квадратичная.
Ну просто все квадратичные полиномы от x, y же.
Может быть, не полином, а моном.
Ну, моном.
Да, да. То есть утверждается, что на самом деле можно взять, можно отправить. So we should normalize it, and then we should take all xi times xj, yeah, and then we shall take all plus I times xj for all 0 using I and j. So yeah, you should have that after multiplying by -1, it will be correct. And it's clear and connected because you multiply here by -1 and here by -1. And actually, it's not hard to see that you can recover from these numbers. No, it's some exercise that it is really. So it will be embedding in n times n plus 1 half. And let me so let's check. But it's very it's clear. Check. It is okay, and for CPM, what is the formula?
Probably want to do some computation.
Yeah. For CPM. So we have to like see again. And it will be the equivalent. And from there, we again normalize it. And here we have the I times j bar for yeah, and this is symbolic. And then
Зачем брать сопряжение ZG?
well, because you want the action of S1 will not change this coordinate, and you multiply by alpha bar, and so by 1. Yeah. And now I state, and now our theorem states that we can just some linear function on Rn, compose it with embedding, and we will obtain worse function. But now I want to write explicitly Morse function on CPM. So okay, let it do the exercise. So it states that f from CPM to R, which is the following, so f 0 to the n, it's some okay, it's 1, we normalize it of course, and we take some constant ci times ci square, where Cn are pairwise distinct. Real numbers. Yeah, so we take this formula and we take here parts like zi to zi bar, which are normal zi square, and we take the sum with some just like arbitrary with some good coefficients. Yeah, these coefficients should be of course real and they're distant. And it states that this function is worse. So maybe that's something to check. So it works. Yeah, let us say that checks that it is Morse. Checks. It's Morse and find plus find critical point in the indices. Yeah. Zero indices. So hint that you should rewrite this function on classical charts and see what happens in charts. Yeah, we have 10 minutes, so maybe I will give you a second exercise and you will do it at home. So the second exercise is for Grassmannians. Yes? Okay. So, and we want to write Morse function on Grassmannian. So we again want to do the same procedure, and so first of all, what we want to do, we want to embed Grassmannian in some Euclidean space. So maybe somebody know how to
Maybe
do
we
this.
can firstly use Blücher embedding
Yeah, it's
to
great.
include in projective space and then apply.
Yeah, then
We
apply
can,
embedding of project space. So yeah, so you can use that in mind that you have Blücher embedding. Maybe let me write it in an invariant way. So you have Grassmannian of k-dimensional subspace of a vector space V, and then you can embed it into actualization of k exterior power of V, and it works as follow. You take some subspace k, and you map it to exterior product. Yeah, so it's Blücher embedding, and then so you take just the composition of this guy, you embed it by Blücher to projective space, and then you embed it to some real space that we don't care about the matrix. And then I again want to so yeah, we have such embedding, so we know that we have plenty of Morse function, so we can take just some composition of this embedding with some good linear function from Rn to R, but let me write this function explicitly. Здесь не видно, что написано.
Да,
Видно?
нет.
So maybe I will erase this. So. So the functions follow, but it's some maybe cheating way that you can consider Schubert cells. So let me remind that for a partition, from one, you have such matrices. You have something here, then you have 1, 0, zeros. Etc. And these ones are stands in I1, I2, I3, etc. columns. And so this is cell which will be known by capital phi, it's just standard Schubert cell. Yeah, then we have its dimension. Which of course we can write explicitly. So yeah, here this is stuff. So it's n minus n plus 1. Times it minus 1 minus 1. And we have its center. So phi is center of 2pi. So center is just the whole stars are 0.
А это матрица сколько на сколько?
Here you have n, and here you have n plus k. Yes. So, and you want to... короче, мы хотим выделить невырожденный минор, как бы n на n. И мы считаем, что он стоит в каких-то столбцах.
А мы выбираем Гроссман Kn, значит, что n плоскости в k плюс n пространстве.
Yeah. So, Gaussian n... sorry. So it's, yeah. Here it's Gaussian k n plus k. Yeah. This is Gaussian, sorry. Yeah, and this is about the form. So your Gaussian is just okay, it's matrices. K times k. So no, it's n. It's a center, and then so the proposition, not so exercise. That first of all you have a function on the space of matrices who are, which looks like follows. So f star of m, it is sum over all such numbers. Di times dot I square of x divided by sum over that I square of x, where that I square of x is following, so over m. Where we do the following, so we take our matrix and we take its E1, E2, E3, etc., En rows, and we take determinant, square of determinant of such matrix. And then, so, и вообще ничего. Yeah, and then we state that, of course, f star define function, define significant function on Gaussian. So it's invariant in direction of UF. It's just this. And it's Morse.
And moreover, so you have the following. So it's critical points are exactly center of cells. Index in this point is just dimension of the cell, and its function is good under embedding of Grassmannians. So if you take functions corresponds to the next, so it's n-dimensional subspace in n plus k plus one-dimensional space, and you restrict it to Grassmannian just n plus k, so you will obtain the function from this Grassmannian. So, and actually it's clear that it is very connected to Blücher embedding, because of course this square of Grassmannians comes from Blücher embedding. Yeah, because Blücher embedding was you take exterior power. Sorry. You all know what? Yeah, in Blücher embedding we had exterior power, but all of you know that if you have some linear map, yeah, of n-dimensional spaces, then if you consider its top degree exterior power, it will be multiplied by a determinant of n. And here's the way how the determinant actually comes from Blücher stuff. But maybe this is some not very easy exercise, but it's just a very implicit formula. But for CPN, it's really not hard exercise. So it's just some easy computations. So yeah, and yeah.
Почему Grassmannian это матрица фактор по UN?
Ну, это выбор, как бы мы выбираем базис, и тогда подпространствие, коверное подпространствие надо выбрать k векторов. Но их разный выбор, выбрать n векторов. Но мы можем на эти вектора действовать в n, конечно, мы будем получать одно и то же пространство.
Почему не GLN?
О, Господи. Спасибо. Да, спасибо.
А если еще на C, наверное, нужно...
Ну, в смысле, ну да, но это все не важно на цели, ну как бы, it's all the same for C or not. But good stuff that for C you have cells only in even dimensions. So from Morse function, both of this example will give you minimal cell decompositions, and so this Morse functions will give you just Betty numbers of your space. Yeah.
This
Just homologies.
This cell decompositions will be exactly
Yeah, here it will be Schubert,
decomposition.
of course. And that's the reason why it's just some cheating way. And for CPN it will be again standard decomposition. Yeah, maybe final comment that, but maybe it's some, maybe it's hard exercise. That there is a different way to write Morse function on Grassmannian without this cheating with Schubert cells. And it's the following. So
we take Cn and let me have some scalar product. Of course, skew symmetric, just some Hermitian scalar product. And then Grassmannian, so you can, from hyperplane, so it will be again K in N. You can construct just projection operator on B. Yeah, using this scalar product. And then I state that you can take just F, you construct F just by formula. You should take, you should take trace of your PV times some diagonal matrix. Times some diagonal matrix C1, Cn, where again the all distant and the and actually it is again good exercise, but like obvious that the function for CPM, which you write, it's exactly like this. The function for CPM is exactly like this. So, but here you can just Google like Morse function of Grassmannian, and you'll have this construction proof.
Можно еще раз? Что тут происходит?
Okay, we fix some scalar product on an n space. Then the subspace define your projection operator on it. So you just decompose Cn as V plus orthogonal complement, and you just project it to V. And then you can define your function as follows. So you can take your projection operator, compose with just this diagonal matrix with some. It should be good. So on diagonal you have distinct numbers and they all are real, and you take trace of it. And the statement that this is statement that it is Morse function. And actually again it will have minimal cell decomposition, so it will lead to Schubert cells. Yeah, maybe let me. Yeah. So check that, if you will think about it, check that for CPM, the formula is exactly like this. So maybe we'll finish here.
В том утверждении, что там, если брать линейные функции, то для почти всех будет функция Морса получаться.
Да.
Ну, там нужно, короче, подумать еще, потому что мы получили отображение как бы с волной из окрестности ямы. И мы отправляем x в линейное отображение на всем РН.
Слушай, можно это думать так, что как бы берешь функцию, ты как бы ты у тебя здесь как бы x и функция f плюс минус сейчас, если тебе так не нравится, то, наверное, можно
Не нравится.
Ну да, нет, по-моему, это сложно исследуется. Но как бы если тебе не нравилось то, что с критическими точками, то понятно, что x это ровно критическая точка функции f плюс вот линейная функция l, где l это как раз минус df от x. Но мне кажется, что здесь не надо об этом париться, потому что у нас как бы, ну, вот, на РН все карты, ну, очень.
Да, я понимаю, но просто я про то, что у нас получается гессиан как функции на исходной. То есть он будет не вырожден, но еще при этом как бы он будет содержать в себе гессиан, который нам нужен, но еще там что-то будет в другом не надо.
Но будет, нет, но это как бы, но тут мы получаем исключительно более сильное утверждение, потому что если бы у тебя как бы гессиан на L был вырожден,